So I'm Dave Redish. So I want to start by thanking the organizers for inviting me. It's been a fantastic couple of days, really exciting. Part of me feels like I want to say, and here's for now something completely different. We'll see. I'm going to kind of make a little bit of a polemic and a little bit of kind of where I think data is sitting, and we'll kind of see where it goes. So first of all, I have no conflicts of interest, and this is funded by NIMH, and this has been funded by NIMH and by NIDA. So I want to start off with a kind of perspective, which is, yes, behavior arises from these complex structures of genetics and pharmacology and your environment and your social structure, but these are fundamentally all translated through the brain. And that means when we look at an underlying dysfunction in one of these structures, things like a genetic dysfunction or something, they are in fact translated, I would argue, through computational dysfunctions in the brain. And what this means is I'm going to make the argument today that we need to be seeing psychiatry as computational dysfunctions, and I'm going to argue in decision making. We can talk about some of that later. One of the things I want to point out is that a lot of what we try to talk about when we do cross-species translation is we're often talking about questions of, are the species are the circuits the same? And I want to argue that when we compare this and we want to compare circuits, because circuits are doing computations, what we want to actually be testing is, are the species doing the same computations? So for example, I'll talk later about deliberation work that we've done. And humans will deliberate over, for example, do I want to go skiing or do I want to go take my family to Stonehenge? Whereas the rats are going to deliberate over food choices. And these two deliberations, even though they are fundamentally quite different, they're on different time courses, one is linguistic, one is, food, they have certain properties. They access homologous structures. They have certain computational properties that are the same. For example, we don't deliberate by creating a quantum mix of skiing down Stonehenge. What we do is we create a concrete image of Stonehenge, of taking the family to Stonehenge or taking the family skiing. And then we alternate. We evaluate these serially. It turns out rats also evaluate these decisions serially when they are deliberating between choices. And the reason is because there is a fundamental computation to deliberation that we can access. So one of the points I'm going to start with is when we're doing cross-species translation, a large part of the key to the puzzle, I'm going to argue, is we have to get the ethology right. And what do I mean by that? So for example, if we take a classic rat behavior experiment called the Mazur adjusting delay discounting task, where you have a rat is going to going to do something which has a choice between either taking a smaller amount of food quickly or a larger amount of food after a delay. And then theoretically, you should be able to titrate the delay so that if it takes the larger delay, you raise the delay, make it less valuable. If it takes the smaller, you lower this delay, you make it more valuable. Theoretically, the rat should balance delay against food. This is a classic story about rats and behavior. It doesn't work. And in fact, there's a beautiful paper from Barry Everett and Trevor Robbins' lab, Rodolfo Cardinal's the first author, where they analyze quantitatively rats doing this task on levers. And yeah, okay, over months you get impulsive rats and non-impulsive rats, and that data is valid. But if you're trying to say at a moment in time, do the rats actually make a choice that looks like this? The answer is no. They drive the delay way up, and then they drive the delay way down, and then it's just garbage. However, if we take that same task and we move it into a spatial paradigm, where now the rat runs up this central track, turns one direction for food and after a delay, and another direction where it gets food immediately, suddenly the behavior looks beautiful. And this is real data from our lab. I'm not going to actually talk about this experiment. I just want to give this as an example. What we have here is the delay to the larger later reward as a function of lap. And what you can see is the rat is alternating for a couple of laps to kind of figure out which side is delayed, because of course we counterbalance that. How much is it changing, because we change that. And then it titrates either down or up, and then it holds it constant, alternating beautifully. Rats understand space. I will say when we tried to translate this task to humans, we were unable to do it. Humans like levers. But this isn't actually something that is purely, it's not just that rats are dumb. Okay, every species has a preferred ethology, and when you're trying to get the computation, you've got to get that species has to be right. This is a classic psychology experiment from Wason and Johnson-Laird in 1972. And the idea is that I'm going to give you a rule. This rule is that if there's a vowel on one side, there should be an odd number of the other side of one of these cards. And then there's a set of cards, and you ask the subject which card you have to flip over in order to test the rule. And of course, everybody flips over the A, obviously. Nobody flips over the B, but the vast majority of people flip over the 7, which is wrong. The correct answer is you have to flip over the 2 because that's the counterpositive. Nobody cares if there's a consonant on the other side of the 7. But if there's a vowel on the other side of the 2, then you're wrong. Okay? Humans really very bad at this. Okay, let's take a different task. You're a waiter in a bar. There's a father and his underage child drinking. There's a friend, one of whom ordered a whiskey, one of whom ordered a Coke or soda. What do you have to do to make sure nobody's drinking illegally? You card the whiskey, and you make sure that this child is not drinking alcohol. 100% of American adults gets this one right. It's the same task. Right? Getting the ethology right is important. So the two kind of starting points that I'm going to do today from my talk is that what we want to be doing when we translate across species is we want to be thinking about computation, not circuits, not task, not disease, computation. Are they doing the same computations? And second, that framing matters, that when we're talking about a species, we have to know what is the ethology. You know, I always joke that, you know, I can ask my rats how they feel about things, but they don't answer me, right? We have to get the ethology right. So if we want to do this translation, we have to get it into a way that that species understands, whether it be mouse, rat, undergrad, or human. So I'm going to give two examples today. And I'm going to kind of work through them in detail, and we're going to talk about the mechanistic neuroscience that we've been doing on this. One is I'm going to do kind of from humans to rats and mice, and a kind of deliberation automation story. And second, I'm going to talk about a task that we call Restaurant Row, which is basically a translation from rats and mice to humans. And then after I've done both of these, I'm going to come back and do a little bit of kind of polemic on like where I see the question of computational psychiatry, which may or may not open up a lot of argument and discussion. So, okay, deliberation and automation. So this starts actually from observations in humans in the 1950s, where HM, of course, had a hippocampal lesion, and then people like Brenda Milner discovered that HM, even though he had a hippocampal lesion and could not do declarative memory tasks, was able to do procedural tasks like drawing a star in a mirror. I don't know if you've ever tried this. This is really hard. It's really, really hard to do. But with time and practice, you can learn. And HM could learn, even though he never knew that he learned. He would say, I can't do that, and then he would say it's really easy. So a classic task might be, for example, in humans, might be something like the serial reaction time task. So the serial reaction time task, you tell the human, just push the button that lights up. And unbeknownst to the subject, that button lights up in a sequence. In this case, 1, 3, 2, 4, 5, 1, 3, 2, 4, 5. I hope everybody can see the sequence. What you find is that in humans, there are two observations that prove that they understand the sequence. I apologize for the dark. It was much brighter on my screen. One is that the reaction time goes down as they experience these blocks of sequences, but when you give them a random sequence, it pops back up. So they've learned something about the sequence. And this is the anticipatory movements, which increases and then, of course, collapses with the random. However, you can also ask the subject, was there a sequence? And they could tell you, well, yes, I saw a sequence. It was 1, 3, 2, 4, 5. It turns out these two are, in fact, dissociable. You can have people who can tell you the sequence but don't show anticipatory movements, and people who show anticipatory movements but don't show the sequence. And the argument is that you've got these two kind of memory, they were called memory systems at the time, I'm going to call them decision systems, but there are these two systems that are quite separable. It turned out that this tracked an old data set, an old kind of argument in the rodent literature, which is that if you train an animal to run from the south arm to the west arm of a T-maze, there are two algorithms that this animal could be using to make this decision. One is the animal could say, okay, I know where I am, I'm on the south arm, I know where I want to be on the west arm, what do I have to do that? I need to turn left. There's a kind of map-based logic. And this came from Edward Tolman, who argued that rats use cognitive maps. In contrast, at the same time period, so this is the 30s and 40s, Clark Hull, so Tolman's at Berkeley, Hull's at Yale. So Hull says, no, rats aren't that smart. What rats actually do is they just say, when I'm put on the maze, I turn left. You get a stimulus response, an action chain, stimulus response action chain. Now, of course, this task cannot separate these two theories. What you need to do to separate the theories is essentially flip this maze around. And this is from a 1992 paper, although there was some stuff in the 70s and 80s that laid out and started to see this. Kind of the cleanest experiment was really from Packard and McGaw in 92, where they trained a rat on a plus maze. The rat experienced the whole plus maze, and then they trained the rat to run from the south arm to the west arm. And what they found is with limited training, when they put the rat on the north arm, it took a different action to get to the same place. This rat is doing a Tolmanian, I know where I am, I know where I want to be, how do I get there? Different action, same location. With additional training, the rats became Hullian. They started on the north arm, they said, oh, I'm on the maze, I turn left, they take the same action and end up at a different location. Notice, it's not that one of these is right and one of these is wrong. They both solve the task that we gave the rat. Right? In fact, one of the things that's fun about this is you then go back and look at this non-replicability, by the way, right? This was a non-replicable theory argument, right? It turns out Tolman is interested in learning, and so he's always looking at the beginning of training, because once they know what they're doing, that's boring. And Hull is only looking at the end of training, because then he says, if it's early, I can't quantify it. They're not doing the same thing every time. And so it turns out Tolman was always looking early in training, and Hull is always looking late. So we set out to basically connect these two pieces. And we developed what we called the left-right alternate task, which was originally developed by Neil Schmitzer-Torbert, who was actually my first graduate student, and then Adam Johnson and Matt Vandermeer kind of pushed it into that first stage that I'm going to talk about. So what we have here is a central track, and the rat turns, I don't know, does that work? A central track, and the rat turns either left for reward, right for reward, or alternate for reward. And importantly, when we alternate, we're going to have the alternation is that you have to do the opposite of what you just did. So if you are in an alternation contingency and you just keep going left, you only get rewarded the first time. So these three are all orthogonal to each other. When we started this kind of version 1, we simply changed the strategy on any given day. And I love this point. This was about 10 years. And what we had here is simply we called it a multiple T task. The animal ran through a central track and turned left for reward or right for reward. And what we found is there was something funky happening at this choice point. That is, there was extra time being spent at this choice point on the early laps, but it automated over time, and the lap time normalized over time. In version 2, we put a strategy change midway through the session once we had the rat trained up. And now what we found is that the rat would, we'd have kind of there'd be early learning as the rat learned which contingency was starting. And then when we put the switch in, the rat would drop to perseveration. Importantly, this is not chance. This is perseveration. This is what the rat is going to do, this 0.6, or 1/6, this 1/6 right here, is what the rat would do if it continues doing its old strategy. So the rats do not have ESP. We've proved rats do not have ESP. This is a good thing. It's a joke, but the truth is, of course, with any experiment, you're trying to make sure that the rat is not sneakily seeing something that you are accidentally communicating to it. In the most recent version that we've done, which was developed by Brendan Haas, which is in his thesis, and the papers are out for review, what we actually switch is the strategy changes every 30 to 40 laps. And we see the same thing where you get a drop to perseveration, and we can see this same increase. It's actually a thing I'm going to talk about called vicarious trial and error. I'll talk about it in a few slides, which increases basically after this, at this moment of strategy change, at this moment of confusion. So vicarious trial and error is a behavior that was first observed in the 1930s. It was first observed by Munzinger and Gentry. I always want to cite this abstract because this is Evelyn Gentry. You'll notice something missing from the first paper. To be fair, I don't think it's a woman in science thing, although she was a woman in science in 31. I think it's a grad student has left the lab thing. But in any case, Munzinger later said, I really should have put her on that paper, so give her credit. And then Tolman in the 30s and 40s. And what they argued is that this was about the animal thinking about the future. It's really, honestly, the only thing to do is to see a little movie of it. And I want to emphasize this is just a behavior. We'll talk about the neurophys in a bit. So this is just 4 laps, or 3 laps picked out of a whole bunch. And yes, those are Lego bricks. We make all our mazes out of Lego bricks. They're the perfect thing for rat mazes. So that was a left to right. Here's a right to left. And now I want to show you what happens on here we go, on this lap. The rat comes up and it just anthropomorphically looks like it's deliberating over choices. And now you know what you're looking for. You can really see it. So I want to emphasize something that's apparently been a point of confusion in our presentations, and that's on us, so I want to make sure it's clear. When we are analyzing our data, and all of the data I'm going to talk about, I'm talking about VTE, or vicarious trial and error, laps. I'm not going to talk about the moment of vicarious trial and error. I want to take laps on which vicarious trial and error exist, and we're going to look at the information processing through that whole lap. Apparently that has not been as well communicated as I would have liked. So what we're going to do, just as an example, is we're going to take times the rat is at the choice point. And by the choice point, I define kind of this final approach and then the choice point itself. We're going to ask what is represented within the hippocampus at this moment. And the hippocampus, for those of you who are not neuroscientists, I know there's a variety of people in the audience here. The hippocampus is a brain structure in the rat that represents location. It represents, to a first approximation, the spatial location of the animal. And it has other things as well. But the cells in the hippocampus fire in a given location. We can take the large ensembles of neurons that we can record, say 100 cells simultaneously, and we can decode from that ensemble what is the position being represented at a moment in time. So we're going to take the moments when the rat is in this space here and ask what parts of the maze is it decoding to. And these are, in fact, as I said, place cells. The vast majority decodes to the choice point itself. But there's a little bit of decoding ahead of the rat at the left and right sides. And if we look on whether it's the chosen or the unchosen side, the vast majority of that is in the direction the rat's going to go. Even though the rat is actually at this location, I can predict where the rat's going to choose because the hippocampus is somehow representing that future. Now, this includes both those vicarious trial and error laps and also the run right through laps that you saw. When we split those, what we find is there's increased representation of those future goals during the vicarious trial and error laps, which is basically stretched out and stolen from the choice point. It's almost as if there's a little bit of activity kind of pushed ahead. And that chosen, unchosen loses significance. So this decreases. This is not significantly different from each other, but these here are. So go ahead, Bekele.
So maybe the units, like when you said the coding, do you actually mean the number or the number of cells or like the...
What I'm decoding is that we take a probability. So it's actually, we're doing a Bayesian decoding. So the Bayesian decoding gives us a probability. We're asking how much of that probability distribution over the whole maze is in that part of space. Does that make sense?
Yep.
Thank you. That's very helpful. So it turns out these are not actually kind of going in both directions, stretching out. These are actually sequences. So I should point out that this discovery, this is from Andy Papali's 2016 paper, but in fact this discovery was made by Adam Johnson in the lab. I really want to give him credit for it because I didn't believe it when he came to me. Which is, of course, the way that good labs should work, right? The grad student comes in and the professor says there's absolutely no way that's true. And of course, it turns out to be true. And then you get to talk about it and give him credit because he was right. So this is data from Anupam Gupta. And what he did here is we actually looked at the firing of the individual cells at moments in time, at very fine time scales. So here is the path of a rat on one of our journeys. I don't know if you can see the gray dots are the path throughout the whole figure 8 maze. This path is coming up. This is our choice point space. And you can see a couple of these vicarious trial and error events. Again, we're going to analyze over the whole lap. But we're going to look right now at a moment in time. And what we see is we've plotted each of these cells, which likes a specific location in the environment, at the center of its place field, at the center of that location that it likes. And what you can see is a sequence running from the rat to the goal. Now, an interesting point, bringing up because we've been talking about oscillations, in fact, the hippocampus runs an oscillation, a theta oscillation, which is about 6 to 10 hertz. It's approximately 7 hertz. And in fact, what we're seeing is this sequence is one theta oscillation. And you can see kind of sweeps forward along the path of the rat. So that suggests that these sequences are actually going to the next goal. But right now, we've got these two goals separated. If it's really going to the next goal, we need to know if it goes actually just to the next thing in that journey. I mean, if I'm sweeping this way, is it just that it hits the wall and that's what stops? Or is it something about the goal I want to get to? And to get there, we developed a task. This is work by Andrew Wickenheiser, who's actually now at UCLA as a junior faculty. And what he developed is this beautiful foraging task. So the rat runs around this circle. I'll do this. The rat runs around this circle, and sometimes it runs one step, sometimes two, sometimes three around. I'm not going to get into all the details because I want to make sure that there's time to talk about other things. But we can take the one-step, two-step, and three-step journeys, which I will point out are decided by the rat. This is not us forcing it on the rat. It just happens to be sometimes the rat does one step, sometimes two, sometimes three. And we do see sequences. This is a sequence of the place cells, just like you saw with Anupam's data, this time running from yellow to red instead of blue to purple. You decide what you're going to fight with grad students about. The X is the location of the animal. Again, running from where the rat is, sweeping, including representation of the goal. So what we did is we took this foraging cycle and we rotated all of the data so they all started at the same location, right? Just for analysis. And what we have then is a one-step journey, a two-step journey, and a three-step journey. Notice the first part are in fact identical. And we can match these for velocity and acceleration so that they're in fact matched identically. And what we see is that on the three-step journey, these sequences go on average significantly farther than the two-step or the one-step. They are going farther ahead on average. It could be just that this is a long journey, so we have this beautiful control where we now align them at the end. And when we align them at the end, again, the last segment is now identical, and now there's no difference at all. These sequences are going to the animal's cognitive next goal. And the Anupam data that we were looking at is running to this goal because that's the next goal the rat is considering. What we're going to see is that this vicarious trial and error is the rat considering alternate goals back and forth. So it turns out that this theta cycle actually is a regular thing that runs as the rat approaches that choice point, as the rat's in the choice point, and as the rat makes this decision. And so John Lispin argued for years that, in fact, this sequence was a fundamental property of the theta cycle. And this is from a 2009 review that he and I wrote together. So what he argued is that there's kind of a first part, which is you are here, and then it runs forward. So if the rat is at this purple place field, you'll get a purple, 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 blue, green, yellow, and then as the rat moves forward, the sequence changes, right? You are here, sweep forward. You are here, sweep forward. And Brandy Schmidt, I shall point out, right, this is the IPAM data, right? You are here, sweep forward. And you can actually, it looks like there's almost 2 parts here. And in fact, Brandy Schmidt, who's a postdoc in the lab, analyzed her data by decoding the first half of the theta cycle versus the second half of the theta cycle. And what you see is that the first half represents where the animal is, and the second half represents this future. This really is every theta cycle. You are here, sweep forward. It turns out, however, that when we look in depth at these theta cycles, in fact, they're asymmetric, something that was first observed in Yuri Bushaki's lab. And what we find is, so that means that the you are here and the sweep forward are different lengths. And so now what we could do is we can actually, it's very easy to get millions and millions and millions of theta cycles, whereas a good day when you get enough cells to do this kind of decoding is tricky. So instead of, we're going to do this next analysis on the theta cycle length itself. We have data, I'm not going to talk about it here, that shows that the average length of the sequence is proportional to the length of this theta cycle, and that the average number of gamma cycles within that theta cycle is proportional to the length of the theta cycle. Those are both published. Those are Anupam Gupta's data. But what Brandy did is, so Brandy has a task, which I'm going to talk about later, where the animal has a delay to the next goal. So the goal is physically the same distance, but there's a temporal delay to the next goal. And the rat is informed. It knows what that delay is. It's actually a pitch of a tone that tells it the delay. High pitch means it's going to be a long delay. Low pitch means it's going to be a short delay. I'll talk about that later. But what she found is that the you are here part is unrelated to the delay, but the sweep forward part is linearly related to the delay until it kind of maxes out. This really is, you are here, sweep forward to the next goal. And interestingly, the fact that it's going to delay tells you it's not just space, it's some sort of episodic future computation component. So this turns out that what we have is we can come in and really break down, and I could go on for hours on this, I'm not going to, break down this whole hippocampal process that underlies this navigation. In fact, we know now that it's in fact prefrontal cortex sending a ping to hippocampus. Hippocampus runs that sequence forward, and then the nucleus accumbens core actually evaluates it. That's data I'm not going to show you, but I can if anybody wants offline. So what's happening in this other strategy? So if we look at these paths of the rat carefully, what we find is we can see this kind of automated anticipatory behaviors also appearing. So here, for example, is from Brendan Haas's data, a rat running through this central track and then turning. In fact, we're looking only at the left choices on this one path. There is a VT on an early lap, but with later laps, the paths become more and more regular. And we can quantify that, and what we find is that that, of course, drops off, but then it has a slow growth as the animal automates that strategy. And interestingly, that is quite counter to the vicarious trial and error. These are not actually correlated. There's the big drop that happens with this, but then this is, for all intents and purposes, flat, whereas this is highly significant coming back up. So supposedly, this is the procedural system. This is computationally, the human literature would tell us that this is supposed to be a recognize the situation and release an action chain. Okay? If that's computationally true, we can make specific predictions about the information processing that should happen within this neural system. For one thing, the cells should not represent space particularly. They should represent the important information, right? This is stimuli that you're selecting out to associate with the actions. And what we found, this is work by Neil Schmitzer-Torbert, what we found is that when we take a spatial task, like the multiple T task, rats run up the central tract, turn left or right for food, knowing where you are tells you what to do, and we compare it with this spatially run non-spatial task. I love this task. So in this task, the rat has to count to 5. So it starts here, goes 1, 2, 3, 4, 5, it gets food. That means it's now here, 1, 2, 3, 4, 5, it gets food. So the reward site precesses around the task. We call it take 5 because it's in 5/4 time. There is a jazz fan in the audience. You can always tell the age of the audience because there'll be 1 or 2 people who actually get that joke. Anyway, the point is, what we measured is we measured how much, how good we were at being able to decode the spatial information. And what you can see is the larger our ensemble size, this is early data, but so it's relatively small ensembles, but the larger our ensemble size, I should point out, this is recordings from the dorsolateral striatum. I realize I didn't say that. This is recordings from the dorsolateral striatum. But the larger the ensemble size, the better a recording we have. The better spatial decoding that we have on the multiple T task, but on this take 5 task where space is not informative, there's no spatial information at all. Right? This is contrast. You do this task in hippocampus, you get space no matter what. We've done that. I could show you lots and lots of examples of not sweeping to the goal, but absence of evidence is not evidence of absence. So instead what I'm going to do is just show you how much of the decoding is ahead of the animal versus behind the animal. In hippocampus, on this data, what you see is an increase of the decoding ahead of the animal on the early laps. This is from that original data where the early laps were those vicarious trial and error laps, not necessarily the vicarious trial and error moments, but the laps. And you see increased decoding ahead of the animal in the hippocampus, but not in the dorsal striatum. The dorsal striatum is showing where you are. It's what do you do at this moment. And finally, the whole point about this procedural action is release of a ballistic movement, right? Think hitting a baseball. Right? Hitting a baseball, you make the decision to swing, but the actual moments of the swing itself, it's not really, you're not making decision points at each of those points. It's a ballistic moment that you've practiced over and over again. So the best data on this is actually from Anne Grabiel's lab. This is from a Smith and Grabiel paper in 2013. And Anne had been identifying that at the beginning of one of these journeys, you see this burst of activity in the dorsal striatum, which her lab calls task bracketing. And what they found, the Smith and Grabiel lab I particularly like, because what they found is on laps that do not have vicarious trial and error events, which they call deliberation, non-deliberation events, you see a burst of activity in the dorsolateral striatum at the beginning of the run, which really suggests we have these 2 decision systems. We have one decision system making decisions by sweeping forward on the lap as the animal deliberates over its choices, and a second decision system which kicks in at this moment of ballistic initiation. And we've replicated this. Replication is important. And we've replicated this on our left-right alternate task. This is a very complex figure, and I apologize for it, but I'll point out the important point, the important data. So this is work by Paul Regier, and what we found is that as the animal leaves this, called the I don't remember even what EZ starts for, but something zone, probably end zone, but who knows. But it's the zone at the beginning of the journey. The animal takes a ballistic movement to start doing this as it learns these late laps. So this is a single switch LRA task. The animal gets one strategy early, and what you see is development of task bracketing in the dorsolateral striatum, not the dorsal medial striatum and not in hippocampus. With time, when the animals kick out of the strategy, that task bracketing goes away and then comes back. So what we have is this shift of a deliberative strategy at the beginning of the day, shifting into a procedural strategy, kicking them out where we go back to a deliberative strategy to a procedural strategy, kicking them out of that procedural strategy, they start to go back into a deliberative strategy, and then they automate back into a procedural strategy. So what we have here is we are able, by taking this computation and putting it into an ethological version that the rats understand, we can see that deliberation really is this whole computational process that the psychologists suggested it was when they were first looking at people like HM. And second, that this procedural behavior is, again, this very specific computational process that you can get to from those original psychological hypotheses. Now, in the interest of time, I'm not going to talk about either the ventral striatal orbitofrontal data, about deliberation and how that represents reward and evaluation, or the prelimbic or prefrontal cortex that encodes strategy. Anybody wants to talk to me afterwards, I can talk about those as well. But I want to now take this and shift gears and go to the other side and give you another case study where we're going to take data from a rat and mouse experiment and translate it into humans. So Adam Steiner originally developed this to look at the question of regret, which I'm not going to talk about today. But this is Brian Sweiss's version. We call this restaurant row. And so what happens is the rat or the mouse runs around this rectangle encountering restaurants. There are 4 different restaurants, each of which provide a different flavor of food. In this case, plain, grape, chocolate, and banana. When the mouse enters the zone, it hears a tone, and the pitch of the tone tells the animal the delay to the food. And the animal then can either enter so in the offer zone, the pitch is constant. The delay does not start counting down. It basically is like, well, in this case, 3 seconds, but 3 seconds, 3 seconds, 3 seconds, 3 seconds, 3 seconds, 3 seconds, forever, until the animal either skips it, going to try its luck at the next restaurant, or enters, at which point it will count down. Now, 2 important points. 1, it could quit out of this countdown. Second, the delays are random on every entry from 1 to 30 seconds. So it's really like opening the door to a restaurant, seeing the line, and then making your decision about whether to wait for the food. Finally, they have a limited time. They have 1 hour on the track to get all of their food for the day. So this is an economic task. And we were looking at economics. That's why we were studying this. So this is an economic task where the rat basically has to say, is it worth 3 seconds of my limited budget to wait for plain food, or do I want to try my luck at the grape restaurant next door? Easiest way to understand this task is, again, a movie. I apologize to those of you who've seen this movie already, but it's my favorite movie, so I'm going to play it again. So this mouse took a 6-second chocolate deal. You can see it wait out for the delay, and then it will get its chocolate. And then we will watch it as it does about a lap and a half. So it skips a 13-second banana deal. It checked the banana. Skips a 15-second grape, 20-second plain, not a chance, 27-second chocolate, not a chance, a 5-second banana it will take. And now I want you to see what happens at the 16-second grape that it's going to encounter. Now notice that it skipped a 15-second grape, but watch what happens when it hits the 16-second grape, which I love this one. This is why we'll stop, and then we'll stop. Look at all that vicarious trial and error. Then it hesitates before entering the wait zone. The wait zone counts down, and it gives up. Notice, this mouse wasted a huge amount of time in the offer zone, and in fact ended up wasting its time in the wait zone as well and got no food for that time. So what we find on this task is that every animal we've run on this task, or its equivalent, what we find is that every animal has thresholds for each flavor, and those thresholds are internally consistent. They're consistent between trials, between days, between sessions, etc. So this animal, for example, will enter at a lot of banana trials, but not at, but will skip a lot of those it will enter a lot of those banana trials, but not a lot of the grape trials. And what you find is there's 2 thresholds here, an offer zone threshold and a wait zone threshold, right? The black circles are when the animal entered and then quit. So this animal has a very high banana threshold and a very low grape threshold. This animal likes banana better than grape. Other animals will have different preferences. So, okay, we're going to translate this to humans. Obviously, the first thing you think of is you take the humans and you basically don't let them eat for 23 hours and you make them forage for their food. That's not going to work. So Sam Abram, was doing this project co-advised by me and Angus MacDonald, and Sam was trying to say, what are we going to get the humans to forage for? And then one day she comes into my office and she says, I've got it. Humans forage for kitten videos.
What?
And thank you. Humans forage for kitten videos. And so what we now create is a web surf version of this task where you get a download bar. And the question is it worth, this is the first version without the offer zone, this just has a wait zone, is it worth waiting my 7-second download for my kitten video, or do I want to skip it and try my luck at the ballroom dance restaurant next door? And now we have a version that has offer zones and wait zones, so everything is going to be topologically, computationally identical. And now mice, rats, and humans look the same. And we can actually now talk about these behaviors and match them. So one of the things to remember is that we started this by looking at all these mouse and rat behaviors, and we know a lot about these behaviors. So we see vicarious trial and error laps in the offer zone. Again, laps, we're going to find that stuff happens here just as much as it happens here. And other laps where the rat or mouse runs right through. We have earn trials where the animal comes in and waits, and quit trials where the animal reevaluates something and then makes a decision to quit anyway. Furthermore, we have, because we can do these manipulations in mice and rats that we're not allowed to do in humans, that makes sense, we can actually talk about a lot of the circuitry that underlies it. For example, Brian Swice developed a technique where he could measure the synaptic efficacy from the infralimbic to the nucleus accumbens shell using an optogenetics trick, and then manipulate that synaptic efficacy. If you decrease the synaptic strength from the prefrontal cortex to the shell, you basically screw up the wait zone behaviors, but not the offer zone. Wait zone behaviors are somehow dependent on prefrontal override of an accumbens shell. How's that for 1960s psychology? Brandy Schmidt manipulated the prelimbic cortex with dreads in rats, and what she found is it disrupted the vicarious trial and error behavior that happens in the offer zone. So we have infralimbic shell driving wait zone behaviors and prelimbic behaviors driving offer zone behaviors. Furthermore, this is for Sarah, it was actually in the slide originally. So we did a cocaine and morphine manipulation on cohorts of mice. And what we found is that cocaine affected the offer zone and morphine affected the wait zone. These two different, the two drugs have fundamentally different effects on different neural circuits, right? And because we have these neural circuits, we can make all these connections. So why is this all useful? Because now we can start to look at human behaviors and complexities in those behaviors. I'm just going to give you one example from a recent science paper that Brian Swice led, basically reanalyzing Sam's data on humans, Brandy and Kelsey's data on rats, and Brian's data on mice. So sunk cost is an economic fallacy whereby you basically make your decision based on how much time you've already spent. And the idea here, what we realized is that we could look in the wait zone and take some analysis point and ask, what's the likelihood of waiting out that delay? So imagine you have a subject that took a 15-second deal, 5 seconds are invested, there's 10 seconds to go, and we're just going to ask, what's the likelihood the subject quits within that, or stays, does not quit, within that 10 seconds? We could also look at a 25-second offer. So after 15 seconds, this point is now identical. The futures here are the same. The only thing that's different is the past. And what we're going to ask is there an escalation of commitment? This is a little complicated, this graph, but let me take you through it. So we're going to take, this is the rat data. We're going to take on entering into the wait zone, what's the likelihood of sticking out when you enter at 30 seconds? It's quite low. These rats basically usually quit. They don't stick out that 30 seconds. And we can create essentially a psychophysics curve over that. This is averaging all of the different flavors, but it works if you do individual flavors as well. It's hard to get that much data. But if we look 1 second in, what we find is there's a vast escalation of commitment. So this point here is the same as this point here, just 1 second later. And if the rat has not quit in that first second, it's much more likely to stick everything out. More importantly, these 2 points, this 29 seconds to go and this 29 seconds to go, have the same future. The difference is that this point the rat has waited 1 second. And so what we can do is we can fit slopes to this, and what we find is the longer the animal has waited, the more likely they are to wait out the delay, even for a given delay. All 3 species are showing sunk cost behaviors. The cool thing about this is we can also do the same analysis on the time spent in the offer zone, right? Basically, if they spend a lot of time deliberating in the offer zone or only a lot of time deliberating in the offer zone or only a little time deliberating in the offer zone. And now we find there's no effect at all. Sunk costs only start to accrue after the animal commits to the choice. To me, that's a huge result because this is something people have talked about in the human literature, but not in the non-human animal literature. In fact, sunk costs were something that was thought to be solely a human behavior. It's not. It exists in rats and mice, and the only reason we were able to find it is because we created a computationally parallel task that had all these pieces. So I want to point out that this is not a simple thing to do. This is actually, so this spring 2014 is actually when this paper is published. In fact, the work that Adam Steiner started in the rat was back in about 2012. And so we went through and we had a rat version, and then we created a human version, and then we created a mouse version, which turned out to be different. So then we had to go back and redo the rat version, and then we had a long debate right here about whether we publish the paper or go back and spend a year redoing the human data. I'm really glad that we decided to go back and redo the human data with the right match.
Because you already sunk so much time.
That's right, exactly, because we had sunk so much time to it. But also because I don't think we would have gotten into science with just this. I think we needed this piece. But yes, because we had sunk all that time to it. Sometimes sunk costs aren't necessarily, there's useful things to them as well. How am I doing on time? All right, then I'm going to, are we 5 or are we? Okay, then I'm going to skip this. Ask me about the MTurk stuff later. We'll come back. Anybody who wants, we can talk about MTurk later. So I want to spend the last bit then talking about the implications for psychiatry. So I like to think of this as an engineer's view of psychiatry, because what I want to argue is that the key to psychiatry is actually to take a reliability engineering take on all of these. So you take something like RDoC. RDoC is a great description of psychology views on kind of cognition and decision making and processing, but it's not going to get you to psychiatry, because it's not that threat assessment is the problem. It's that there's a problem with threat assessment, and we need to figure out what those problems are with threat assessment, for example. So we need to think about what are called failure modes. And I apologize for the term. I know it's not a PC term to apply to people. I'm not implying that anybody's a failure if they have a psychiatric issue. The failure mode is the technical term from reliability engineering. When a bridge falls down, one doesn't say, oh, it didn't feel good about it, right? One goes in and says, what was the flaw? Where was the failure mode in the system, right? In this case, that the gusset plates were built wrong and had rusted out. And so when we have this kind of reliability engineering language for a system like a bridge failure, we can then go in and we can guide treatment. If we know that the bridge failure arises from a combination of excess weight and too low strength, we could strengthen the bridge, or we could limit the weight, or we could do proper inspection to make sure that the gusset plates aren't actually bent if we knew gusset plates were a potential problem. Right? We need to know what the failure modes are. And so let me take as a concrete example OCD. So let's take actually not OCD, but going back to check to make sure your door is locked. And so one possible reason for this might be an imbalance between these planning and deliberative modes, these deliberative planning and habit procedural modes, where you might have a problem with a response inhibition that says, yes, okay, I know that I have a procedural thing that's working, but I need to shut it down. But it could also be that, in fact, it's a planning problem, that you've got some issue where you've locked the door and you're not sure if you locked it. So I like to think of this like, what if I didn't lock it? Like, I'm only 90% sure. I'm only 20% sure I locked it. I should go back and check. I like to think of this as the absent-minded professor problem, right? I don't know how many other people have this. This is one I have really badly. And so, you go, you check the lock, you lock the door, you walk away, you're down the hall, and you're thinking about the test you're writing that day, and suddenly you have no idea if you've locked the door or not. But it also might be that you're 99% sure you lock the door, which is what we all are, and then you have an over-intense anxiety prediction. One of my colleagues who works with OCD patients told me a story, and I have to tell this because I love this. If the patient left before his wife, it was fine because she'd locked the door and it was her responsibility and he trusted her. But if she left first, he couldn't leave the house. Because if he left the house, he'd only be 99% sure he locked the door. And that meant there was a 1% chance the door was unlocked. Somebody could sneak in, plant a nuclear bomb in the middle of his house, blow up the city, ground zero would be his house, and he'd get in trouble. That person has an anxiety problem and probably needs some help there. I want to point out these are all computational failure modes. By understanding these decision systems, by understanding these components, we can go in and identify these different things from a mechanistic, theoretical perspective. In the last 2 minutes, can I do 2 more minutes? All right, the last 2 minutes I want to hit this one example because I want to not just talk about diagnosis, I want to talk about treatment. One of my favorite examples of treatment, and this is work by Paul Redish, one of my favorite examples of treatment is contingency management, which is basically pay people not to take drugs. It's one of the best treatments for drug addiction that exists. It works shockingly well. In fact, that's the problem. It works too well. The usual story on contingency management is that the reward it's an economic story. The reward is an alternate reinforcer, and you're basically increasing the cost of the drug. Now, the original contingency management treatment was a $2 gift certificate to a movie from Blockbuster. And people were staying off drugs for those $2. If you increase the price of the drug on the street by $2 a week, there's very little effect. Drugs are basically inelastic at that level. So what Paul and I did is we went and took the treatments that had been done and the success rates for contingency management, which are published, and several examples of price on the street and the elasticity of price on the street, and we compared them. And basically, contingency management works about 10 times as good as it should. And so what we proposed is that actually contingency management is not an economic thing, it's a decision-making issue. It's shifting you from one of these is it worth it decisions into a which one decision. It's shifting you into a not am I willing to pay this much for my drugs, but into a do I want this much, do I want my drugs or my gold star? I can wait for my gold star. If that's true, and I emphasize if because I have not convinced anybody to actually test this, but if that's true, we can make a whole slew of predictions because we understand the mechanisms of this deliberative system. So we could then go in and we know that contingency management should depend on working memory. We can test for working memory. If it's not good, we can train working memory. We predict somebody who has a good working memory will do better on contingency management. Furthermore, we could test on a prefrontal cortex hippocampal connection strength. Right? Sarah was talking about connectome stuff. We could measure that connection directly. And I predict that people who have prefrontal hippocampal integrity will do better on contingency management. Furthermore, we know how to strengthen deliberation quantitatively. We can do things like making the second option more concrete because you're imagining that option. It's easier to imagine an option. This is why the episodic future thinking data that Warren Bickel's been finding, I think, is happening, because he's making the second option more concrete, and it's easier to plan into that future. We can provide reminders. I'm now imagining some sort of smartphone game of, I'm going to work towards my big screen television. Now you can play acceleration games on all these things. You can do this whole kind of game on your points for your contingency management. That should work better than simply, here's some money. And so I want to leave you with 3 thoughts. One is that these diagnoses should really be done in terms of these failure modes of information processing. Second, that treatment should modify that information processing. And I'll point out, I think it needs to be said either through changes in the patient itself or through changes in the environment. Contingency management is a change in the environment, not actually a change in the patient. And that translation across species requires a computational validity to measure across. And that's the key to being able to do this cross-species translation. So I'll end there. Hopefully I haven't gone too far over. And hopefully there's some time for questions. Thank you very much.